our third and final curve sketching example. This one's going to be the most work we've had to do so far, but if you can do this one, you could confidently say you know how to do curve sketching for polynomial functions. We're going to follow the same algorithm for curve sketching we've been using. It's going to be 8 steps, where the first of those 8 steps is to state if there are any asymptotes on the graph of this function. Well, this is a degree 4 polynomial function, and I know polynomial functions are continuous, so this function has no asymptotes. Part 2 asks us to state the x and y intercepts of the function. Finding the x-intercepts is going to take a bit of time, but we could find the y-intercept quickly. To find the y-intercept, we just have to figure out the y value when x is 0. So just sub in 0 for x and evaluate. And that's of course going to eliminate all the terms that had an x, and we're left with just the constant term, that negative 18. So our y-intercept is at the point 0, negative 18. Now, like I said, finding the x-intercepts is going to take a bit of time, because to find the x-intercept, we're looking for what value of x makes the y-coordinate 0. So we set the y-coordinate to 0 and solve for what value of x makes that true. So 0 equals, and then we rewrite the function. And to solve when a function is equal to 0, it's going to be useful to get this function into factored form. And because it's a degree 4 function, that might take a bit of time. We're actually going to have to use the factor theorem and test for zeros to try and find something that may make this be 0, and then do some synthetic or long division to get it into factored form. So if you remember the integral 0 theorem, it tells you if there's an integer that makes a polynomial function be 0, that integer will be a factor of the constant term. It'll be a factor of negative 18. So I'm going to, off to the side here, I'm going to do some rough work factoring this degree 4 function. And like I said, I know that possible zeros are factors of the constant term. So factors of 18 are plus or minus 1, 2, 3, 6, 9, and 18. So if there's an integer that makes that polynomial be 0, it'll be one of those integers. We just have to find one that works. I think 1 actually works. So I plugged 1 in for x. I'd have 1 minus 5 is negative 4, plus 1 is negative 3, plus 21 is 18, minus 18 is 0. And by works, I mean it makes it be 0, right? That's the factor theorem. So I would write h at 1 equals 0. Therefore, x minus 1 is a factor. So what we have to do is divide that polynomial by x minus 1. And I'm going to do that with synthetic division. So I'll set up my table. I'll put the 0 of the divisor here, so put 1 there, and then the coefficients of the function up here, so 1, negative 5, 1, 21, and negative 18. And then I'll do my synthetic division, where I bring the first term down. 1 times 1 is 1, negative 5 plus 1 is negative 4, 1 times negative 4 is negative 4, 1 plus negative 4 is negative 3, 1 times negative 3 is negative 3, 21 plus negative 3 is 18, and 1 times 18 is 18, and negative 18 plus 18 is 0. And then what we have here is our quotient and the remainder. So these numbers here are the coefficients of the terms of my quotient. This is the coefficient of x to the 0, of x to the 1, of x to the 2, and of x to the 3. I can now split that polynomial into its divisor, x minus 1, times its quotient, x cubed minus 4x squared minus 3x plus 18. And now what I need to do is, because this second factor is degree 3, I need to try and factor that further. And once again, we're going to have to use the factor theorem, test for zeros, and do synthetic or long division to do that. So I'll do that in a different color here. We're now going to factor this x cubed minus 4x squared minus 3x plus 18 function. So possible zeros of this are once again factors of the constant term, so plus or minus 1, 2, 3, 6, 9, and 18. Now I just need to find one of these that makes this polynomial be 0. 1 doesn't work, 2 doesn't work. How about negative 2? If I plug negative 2 into this, I would get negative 8 minus 4 times 4, so minus 16. Minus 3 times negative 2, so that's plus 6, plus 18. Hey, I think this works. Negative 8 minus 16 is negative 24. plus 6 is negative 18, plus 18 is 0. So negative 2 actually makes it be 0, so I could divide the polynomial by x plus 2, and that'll get me into factored form. So I'll write, I have to call this function something. I'll just call that function f at x. So I'll write f at negative 2 equals 0. Therefore, x plus 2 is a factor. So divide it by x plus 2. Once again, I'll do that using synthetic division. I'll set up my table. I'll put the 0 of the divisor here and the coefficients of the polynomial up here. So 1, negative 4, negative 3, and 18. And I'll just do the synthetic division quickly. Okay, good. So we got a remainder of 0. That means we did it properly. X plus 2 is in fact a factor, and its quotient is x squared minus 6x plus 9. So what I can do is I can split this x cubed polynomial into its divisor, which was x plus 2, times its quotient, which was x squared minus 6x plus 9. And then that last factor, which is degree 2, we could factor that further. What numbers multiply to 9 and add to negative 6? Well, it's negative 3 and negative 3. It's the same number twice. That's actually a perfect square trinomial. It would go to x minus 3 times x minus 3, which I could just write as x minus 3 squared. Okay, that's fully factored. Now from the fully factored form, we can pull out the x-intercepts. Well, what values of x make that product be 0? That would be any value of x that makes any of the factors be 0. So 1 makes the first factor be 0, negative 2 makes the second factor be 0, and 3 makes the third factor be 0. So those x values are the x-intercepts. I'll write them in ascending order. It was negative 2, 1, and 3. So I have 3 x-intercepts, and I've got my y-intercept. That's step 2 of the curve sketching algorithm done. Let's move on to step 3 of the algorithm for curve sketching, where we find the critical points on the function. To find the critical points, we have to first find the critical numbers, and critical numbers are values of x that make the derivative of the original function be 0 or undefined. It tells us where the original function has a slope of 0 or an undefined slope. And those are important because they might indicate a local max or a local min point, right? At a local max, right there, the slope of the function is 0. And at a local min, the slope of the function is 0. But it might not necessarily be a local max or min. Keep in mind it could be something like that. Right there, there's a slope of 0 as well, but it's not a local max or min point. So like I said, we have to find the critical numbers, so numbers that make the derivative be 0 or undefined. So we're going to need the derivative. So let me just rewrite the original function here first. And now let's find the derivative of this function. And all we need for this is the power rule. So I'll have 4x cubed minus 15x squared plus 2x plus 21 minus 0. There's my derivative. I'm interested in when is this 0 or undefined? Well, once again, this is a polynomial function. It can't be undefined, but it could be 0. So let's set it to 0 and solve for what values of x make that true. And then those are our critical numbers. Now, because this is degree 3, we're once again going to have to do the factor theorem, test for zeros, and do synthetic or long division. So off to the side over here, I'm going to factor this 4x cubed function. I'm going to have to find a value that makes this 0, and the possible zeros, based on the rational zero theorem this time, would be factors of the constant term. So factors of 21 would be plus or minus 1, 3, 7, and 21, divided by factors of the leading coefficient. And I have to use the rational zero theorem this time because the leading coefficient is not 1. And factors of 4, plus or minus 1, 2, and 4. So I have to do each of the factors of the constant term divided by each of the factors of the leading coefficient. And then those would be the possible zeros of the function. So I'll just list all those numbers quickly here. 1 over 1, 1 over 2, and 1 over 4. 3 over 1, 3 over 2, and 3 over 4. 7 over 1, 7 over 2, 7 over 4. And 21 over 1, 21 over 2, and 21 over 4. Let's see if I can squeeze that in there. All right, there we go. There are all of the possible zeros that are rational numbers. I just have to find one of these numbers that works. So I have to find one of these numbers that makes that polynomial be 0. And I think -1 works. If I plugged -1 into this, I would have -4 minus 15 minus 2 plus 21. That's -19, -21 plus 21, that's 0. So -1 makes it be 0. So I could write the derivative, that's the function we're working with, at -1 is 0. That tells us x plus 1 is a factor. So we divide it by x plus 1. And once again, I'll do synthetic division. I'll just set up my table quickly and do the synthetic division. So I can now rewrite that polynomial, this derivative function, as a product of its divisor, x plus 1, and its quotient, 4x squared minus 19x plus 21. And then that second factor is a quadratic. I should try and factor that further. I'd be looking for numbers that have a product of 4 times 21, so a product of 84, and a sum of -19. And the numbers that satisfy that product and sum are -12 and -7. So what I could do is split that -19x into -12x minus 7x. And I do that because -12 and -7 are the numbers that satisfy that product and sum. And now I can factor that quadratic by grouping, and it'll get into factored form. So take a common factor from the first two terms, I would take out a 4x. And if I common factor from the last two terms, I would take out a -7. Notice I got a common binomial, so I can common factor out that common binomial of x minus 3, and I'm left with 4x minus 7 as my last factor. There we go, that's fully factored. So I can see from that the x values that would make the derivative be 0 are -1, 3, and 7/4. So those are my critical numbers. So critical numbers, x equals, and I'll put them in ascending order, so -1, 7/4, and 3. And if you wanted to write 7/4 as its decimal value, that'd be fine, 1.75. And now what we're going to have to do is find the critical points. So for the critical points, we need the y-coordinate that goes with each of those x-coordinates. So we'll have to plug each of these x values into the original function, right? Our goal is to graph the original function. So at these points, we know the original function has a slope of 0, right? That makes the derivative be 0. But where's the original function at those points? Let's get the y values. So I'm going to need the y value that goes with -1, with 1.75, and with 3. And I'll do that in Desmos just to make this a little bit quicker. So there's the original function. I want to know when x is -1, where is it? And it says at -32. When x is 1.75, where is it? It says about 4.4. And when x is 3. Oh, and it tells me the y-coordinate is 0 there. I already knew that. That was one of the x-intercepts that we got way up here. An x-intercept was 3. So I already knew the y-coordinate at an x value of 3 was 0. But the other two, let's fill in. Okay, so I know these 3 points are potential local max and min points. When we do our sign chart later, we'll be able to classify them as local max, min, or neither to help us do the graph very accurately. But for now, let's actually start plotting what we have on the grid. So we know the y-intercept is at -18, that's about here. We know the x-intercepts are at -2, 1, and 3. And we have 3 critical points. The critical points are at -1, -32. So that's right about here. 1.75 and 4.4, that's about here. And the last critical point was at 3, 0. We've already got that there. So based on these points, we could already do a pretty accurate sketch of the graph, but we'll make sure it's very accurate by also getting the possible points of inflection on this function as well. That way we can figure out where the function is going to switch concavity. And that's what step 4 of the algorithm for curve sketching asks us to do. It asks us to find the possible points of inflection. So a possible point of inflection is going to occur at a point where the second derivative is either 0 or undefined. So I'm going to have to find the second derivative. So let me rewrite the first derivative here. And now if I differentiate this, I get the second derivative. So we'll find the second derivative. I'll use my power rule with each of those terms. I would get 12x squared minus 30x plus 2 plus 0. So there's my second derivative. And I'm interested in when is this 0 or undefined. That will be a possible point of inflection. This is a quadratic. It can't be undefined, but it could be 0. Let's set it to 0 and solve. And I notice all those terms are even, so I'm just going to common factor out a 2 right off the bat here just to make the numbers a little bit easier to work with. So I've got 2, 6x squared minus 15x plus 1. Now to figure out when this product is 0, that would happen if this quadratic was 0. And when can that quadratic be 0? Well, I'd hope to be able to solve that by factoring, but there's no two numbers that have a product of 6 and a sum of negative 15. So I would have to use quadratic formula to try and find the numbers that would make that quadratic be 0. So from quadratic formula, I would get x equals negative 15, so 15, plus or minus the square root of negative 15 squared minus 4 times 6 times 1, all over 2 times the a value, so 2 times 6. So keep in mind, this is the quadratic formula that is going to figure out when that is 0. And if I simplify underneath the square root, negative 15 squared is 225, so 225 minus 24 is 201, so I've got the square root of 201, and this is all over 12. Now when we're graphing, it would be better if we get an approximate value for this. So let's get the approximate values for 15 plus root 201 over 12 and 15 minus root 2 over 1 over 12. And the other one, let's do the minus version of this. So 15 minus root 201, and I get 0.0685, I'll say about 0.07. Now I'm going to have to find the y value of the function at each of those x values to figure out where the possible points of inflection could be. So I'll title this possible points of inflection. It'll be at, and I'll put these in ascending order, so 0.07, and I'll have to get the y value. And 2.43, and I'll need to get the y value that goes with that. Now I'll actually use the exact x values when I calculate the y values, just so I can be as accurate as possible. So I need to evaluate the original function, which I have typed up here, at the 0.07 x value, which is what the 15 minus root 2 over 1 over 12 is, and I get negative 16.6. I can put negative 16.6. And the positive version, that was the 2.43 x value, and it gives me a y value of 2.05. So at these 2 points, I know the second derivative is 0, which tells me there may be a change in concavity around those points. They may be points of inflection. In our next couple of steps, where we make a chart where we test values in the intervals around our critical numbers and possible points of inflection, we'll be able to see if in fact these are points of inflection or not. For now, let's actually plot these on our graph. So I'll plot 0.07, negative 16.6, and that's about right there. That's really close to that other point we had. And I'll also plot 2.43, 2.05, 2.43, 2.05. I don't know, that's about here. So we've got quite a few points on here. Let's make a chart that's going to figure out the concavity of the function and whether the function is increasing or decreasing in all the intervals around these points that we have. So I'm going to combine steps 5, 6, and 7 in the next part. We're going to make a chart that's going to test the value of the first and second derivative in intervals around each of the critical numbers and possible points of inflection. And if we had any vertical asymptotes, we would need those as dividing points as well, but we don't have any vertical asymptotes. So I've got 2 possible points of inflection and 3 critical points. So I have 5 dividing points. So that means I'm going to need 7 vertical lines And the reason why I need 7 is because we always need one on the far left for negative infinity, one on the far right for infinity, and then in between we have to put the x values of the critical points and possible points of inflection in ascending order. So negative 1, 0.07, 1.75, 2.43, and then 3. And I need to test a value within each interval in the first and second derivative, and then comment on what that tells me about the original function. So I'll test a value in each interval into the first derivative, the second derivative, and then make a comment on what that tells me about the original function. So I'm going to rewrite the equations of these three functions here, just so I don't have to keep scrolling back up every time. And notice the equations I put in factored form, because I think that's going to be easier to test values in, but we could have put the standard form version there. Okay, let's pick a value in each of the intervals. I'm going to pick negative 2 in that interval, 0, 1, 2, 2.5, and 4. And now we need to test each of these values in the first and second derivative, and just figure out not what's the value, but whether the value is positive or negative. That's all we care about. So I need to plug negative 2 into the first and second derivative, and I have the equations here, so you could go ahead and do that. But just to save some time, I'm going to get Desmos to do both of them for me. So I'm going to evaluate the derivative at an x value of negative 2, and the second derivative at an x value of negative 2. Notice the first derivative is negative, the second derivative is positive. So I'll record that information here. First derivative is negative, second derivative is positive. And what does this information tell you? Well, remember, when the first derivative is negative, that tells us that the original function is decreasing. And when the second derivative is positive, that tells me that the original function is concave up. So in the interval between negative infinity and negative 1, I have a decreasing function that's concave up. That means it's going to look something like this. How about the next interval? If I plug 0 in, well, I should be able to do this one without having to go to Desmos, because 0 is an easy one to evaluate. If I plug 0 into the first derivative, I would get positive times negative times negative. That's going to be a positive result. So that means I have an increasing function. And when I plug 0 into the second derivative, I would have 2 times 1, which is also positive. So the function is concave up here. So I have an increasing function that's concave up, so it means it looks like this. So notice the function didn't change concavity, but it did change from decreasing to increasing. So that means we have a local min at this x value here. So there's a local min at an x value of negative 1. And what was the y coordinate that went with negative 1? We could plug that into the original function, which we've already done earlier. The y value is negative 32. So there's a local min at negative 1, negative 32. Let's now plug 1 into the first derivative and second derivative and see their signs. If I plug 1 into the first derivative, I will get positive times negative times negative. That's positive. So the original function is increasing in this interval. And is it concave up or down? Let's check the sign of the second derivative. If I plug 1 into the second derivative, I would have 2 times negative 8. That's negative 16. It's negative. That means it is concave down. Notice there was a change in concavity around this x value of 0.07. That means there's a point of inflection there. At 0.07, and what was the y value that went with that? Well, we've already plugged it into the original earlier, and we got negative 16.6. Now let's plug 2 into first and second derivative. If I plug it into the first derivative, I'd get positive, negative, positive. So that's going to be a negative result. So in this interval, the original function is decreasing. And is it concave up or down? If I plug it into the second derivative, let me just get Desmos to do that for me. We already plugged it into the first and knew it was going to be negative, but what is an x value of 2 plugged into the second derivative? It's also negative. So that means that it is concave down in this interval as well. So in this interval, we have a decreasing function that's concave down. A decreasing function that's concave down looks like this. Oh, and I forgot to draw the shape in this interval. And this interval is increasing and concave down. That means it looks like this. So notice between these two sections, there's a local max point. It's switched from increasing to decreasing. So that means there's a local max at the x value of 1.75. So I kind of ran out of room, so I'm just going to draw an arrow showing that at this x value, there is a local max at 1.75. And where's the original function when x is 1.75? We've already evaluated that. Up here, it was at 4.4. So local max at 1.75, 4.4. We have two more intervals to do. I'll plug in an x value of 2.5, and I'll just use Desmos to do this quick. Plug in 2.5 into the first and second derivative. Notice first derivative is negative, second derivative is positive. And let me just do the signs for an x value of 4 as well. So I'll plug 4 in quickly. Notice first derivative is positive and second derivative is positive. So with all this information, we can comment on what's happening to the original function in these intervals. In the interval between 2.43 and 3, the original function is decreasing, and it's concave up, and I know that because the second derivative is positive. So a decreasing function that's concave up, that looks like this. And notice at the x value of 2.43, there's a change in concavity. The function was concave down before, concave up after. So that means that there is a point of inflection at that x value, POI, at 2.43. And what was the y value of the original function at 2.43? We've already evaluated that. It was 2.05. And the last interval, it's an increasing function that's concave up. Increasing, concave up looks like this. The function switched from decreasing to increasing, so I know that's going to be a local min point at an x value of 3. And the y value of the original function at an x value of 3, I believe is 0. Yep, it is. Okay, so let's sketch the graph of our function following all the information we have here. So we know in each interval whether the function is increasing or decreasing, and whether it's going to be concave up or concave down. In the first interval, when x is less than -1, we need to have a decreasing function that's concave up. So it needs to look like this. And then the next interval, between -1 and 0.07, it needs to be increasing and concave up. So it has to look like this. And in the next interval, between that point and that point, between 0.07 and 1.75, yes, increasing and concave down, so it needs to look like that. And then in the next interval, it's between these 2 points. We should be decreasing and concave down. Let's check. Yep, it says decreasing, concave down, so it's going to look like this. And then in the next interval, between these 2 points, we can see that it is decreasing and concave up. So it should look like this. And the final interval, when x is greater than 3, the function needs to be increasing and concave up. So an increasing function that's concave up. There we go. Arrows on both sides showing it's continuous. There's a graph of our h at x function. And if we compare that to the graph that Desmos would give us, notice we have a almost perfectly accurate representation of that function. And just to quickly summarize, in this interval, decreasing and concave up, then increasing and concave up, increasing and concave down, decreasing and concave down, decreasing and concave up, increasing and concave up. And we got all of that from this chart. Okay, that's our last curve sketching example. Hopefully you have a good idea of how to do curve sketching questions for both polynomial and rational functions now. Make sure you go ahead and try the practice questions that go along with this to make sure you get really good at curve sketching.